Hello students, in this class we will be studying about total internal reflection, critical angle, relation between refractive index and critical angle and some application of total internal reflection. Before going to understand the total internal reflection, let us understand the critical angle. What is this critical angle? We all know that when a ray of light travels from denser medium to the rarer medium, the reflected ray bends away from the normal. And this critical angle is the angle of incident in a denser medium at which the angle of refraction is 90 degree. You can see NOB is 90 degree. So the reflected ray is OB. So we can define this critical angle as the angle of incident in denser medium at which the angle of refraction is 90 degree or a refracted ray travels along the interface is called critical angle. Further, when an angle of incident becomes more than the critical angle, there is no refraction, but all incident light is reflected back to the denser medium. So this occurs the total internal reflection. Hence, we define the total internal reflection as the phenomenon of reflection of light when a ray of light traveling from denser medium to rarer medium is sent back to the same medium provided it strikes the interface of denser and rarer medium at an angle greater than the critical angle is called total internal reflection. Here are the two conditions for total internal reflection. The first one is that the light should travel from denser to rarer medium. The second is that the angle of incidence should be greater than the critical angle for a given pair of medii. Let's study the relation between refractive index and critical angle. That is, n is equal to 1 by sine c, where n is the refractive index and c is the critical angle. Let us consider a ray of light traveling from denser medium to the rarer medium. So, from Snell's law, we can write n1 sine I is equal to n2 sine r. For the critical angle, the incident angle is considered as a critical angle, so I can be considered as C, and the refracted angle is 90 degree. So we can write n1 sine C is equal to n2 sine 90 degree. So as sine 90 degree is equal to 1, we can write sine C is equal to n2 by n1, where n2 is the refractive index of rarer medium and n1 is the refractive index of denser medium. When a rarer medium is air or vacuum, we can write the equation as sine C is equal to 1 by n, where n is the refractive index of denser medium. So again we can write the equation as n is equal to 1 by sine C. So from this we can say that this is the relation of a refractive index and the critical angle. Let's talk about some applications of total internal reflection. The first one is prisms. As you all are familiar with these prisms are designed to bend the light by 90 degree or 180 degree, and they make use of total internal reflection. Such a prism is also used to invert image without changing their size. Critical angle for material of prism must be less than 45 degree. Next is sparkling of diamond. You all know how diamond shines when a light falls on it. Let us understand how total internal reflection helps the diamond to shine. The refractive index of diamond is 2.42 and the critical angle is 24 degree. The faces of the diamond are cut in such a way that whenever light falls on any of the faces, the angle of incidence is greater than 24, that is critical angle. When light falls on diamond, it suffers the repeated total internal reflection. The light which finally emerges out from few faces is a certain direction makes the diamond sparkling. Another example is mirage. What is this mirage? You all might have experienced in a hot days while traveling in a car, there is a water on a road far away. When you go nearer to that water disappears. That is because of the mirage. So we can say mirage is an optical illusion of water observed generally in deserts when the inverted image of an object is observed along with the object itself on a hot day. Let's study about optical fiber. This optical fiber is a device which can be used to conduct light along any desired path. This works on a principle of total internal reflection. As you can see in the diagram, it consists of thin transparent fiber made up of glass or plastic known as core. The core is coated with a material of lower refractive index known as Cadling. Now let's see how it works. Consider a ray incident at one end of the fiber. If the incident ray meets the interface between the core and the Cadling at an angle greater than the critical angle, it undergoes series of total internal reflection and finally emerges at the other end as shown in the figure. In the next class, we'll study about refraction through spherical mirror. Thank you.